All right, for geometry, we're doing lesson 2.5, algebraic reasoning. All right, so first up, we're going to go through a review of all the different numbers and types of numbers that we have. Okay, so first, we have the natural numbers, and that's the N that you're going to see. They start at 1 because the natural numbers are also called your counting numbers. So when we count, we start with 1. So 1, 2, 3, 4. Whole numbers are next. Okay, so the only difference in whole numbers is the 0. Okay, that includes a 0 because we can have 0 holes. You can have 0 acne on your face, right? That's cool. We want that. Or that's what we desire, right? Is 0. Next up is integers. Okay, so integers have this Z letter. So the difference there is that we now have positive and negative 1, positive and negative 2, and so on. And the next one is a Q. Those are your rational numbers. Okay, those are fractions. And the irrational numbers are the Q, but they have a little prime in them. Those are the irrational numbers. So they use special symbols. Okay, so we have like the square root or pi, or they're decimals that don't terminate and they don't repeat and don't terminate. They're the ones that just go on and on and on and on. But a lot of times they have those special numbers. All of these, however, are called the real numbers. So that's why we have this chart here. Okay, our real numbers are broken into, we notice they'll split in half, into our rational and our irrational numbers. Those are the two halves of real numbers. And then everything else is inside the real numbers. Okay, so the integers, or let's say the natural numbers, are the smallest there, the 1, 2, 3, 4. Then we get a little bigger when we go into the whole numbers and we add the 0. That's the only difference. And then when we get a little bit bigger and broader, that's when we get the integers. And so we have the positive and negative 1, the positive and negative 2. Okay, and then the Q, that's when, or the rationals, is when we have 3/4, a negative 2/3. Okay, all those go in there. Where the irrational are where we would have pi and the square root of 3. Okay, if we were going to put some numbers in each of those areas. Okay, so this should be review from like algebra and even probably before algebra. Okay, then let's look at some real number properties that we're going to use. We have, first of all, I do want you to notice that it says, we've got to start here, A, B, and C are all elements of real numbers, okay, in order for this to work. The identity property of addition is when we add 0, it doesn't change the number. We had A and we keep A. Identity of multiplication is we multiply by 1. A times 1 leaves us with A. We don't change the identity of the number. The inverse property, okay, if we have A, then we add a negative A, the inverse, and it equals 0. The inverse for multiplication, if we have A, we multiply by the inverse, which is 1 over A, and it equals 1. This might be more familiar if we think of like 2/5 times 5 over 2 equals 1, and multiplying those inverses. Commutative property, we can add in any order. A plus B is the same thing or equal to B plus A. And in multiplication, A times B is equal to B times A. Okay, so those are the same. We can move the orders in any number. The associative property has parentheses in it, but it's what changes inside the parentheses. Okay, we can add A plus B first because it's A plus B plus C, or we can group B and C together, and we can add them first and then add the A to it after. And that's the same thing with multiplication. If we put parentheses around it, we're multiplying A times B first, and then we multiply C. But that's the same thing as putting parentheses around B and C and multiplying those together first, and then multiplying by A. That's the associative property. The distributive property kind of bridges both gaps, right? Because that's when we distribute the number on the outside to the numbers on the inside. So we end up with A times B plus A times C. It uses elements of addition and multiplication at the same time. All right, then we have properties of equality. Some reminders there. The reflexive property is when A equals A. We're just saying it equals itself. The symmetric property. If A equals B, then B equals A. So it is some symmetry. We can flip it. The transitive property. If A equals B and B equals C, then A equals C. Okay, we can kind of transfer that knowledge together and bring those two together. The addition property of equality. So if A equals B, then A plus C is the same thing as B plus C. So we changed out the A for the B. And very similar to the multiplication property of equality. If, again, A equals B, then A times C is equal to B times C. That bridges back to because A equals B and we know it. All right, this little piece over here on the right says there's no subtraction or division properties of equality. Okay, and that's because subtraction is the same thing as the additive inverse, and division is the same thing as the multiplicative inverse. So there are no addition or subtraction and division equalities. All right, let's move on up. Look at this equivalence relation. Okay, is a relationship that's reflexive, symmetric, and transitive. Wow. So an equivalence relation is a relationship that's reflexive, symmetric, and, right, it's and transitive. So the equality of real numbers is an equivalence relation. Next up, the substitution property. If A equals B, then A can replace B in any mathematical statement. Okay, so the substitution property is a lot like, right, the substitution property is a lot like the addition and multiplication property of equality. That's like a restating of that we can use that substitution property and do those. Okay, so information heavy, right? That seems to be geometry these days. Very information heavy. We've talked about this a lot in class. All right, next up is the trichotomy property. Okay, so the trichotomy property. For any two real numbers, A and B, exactly one of the following is true. Okay, one and only one, exactly one of the following is true. A is either equal to B, A is less than B, or A is greater than B. And you're like, well, that makes sense, right? Like that's kind of self-explanatory, but that is the trichotomy property. So example one, okay, we're going to be using these properties today a lot. Name the property that justifies each statement. All right, so example A, or there, yeah, A there, is if 5s equals 60, then s equals 12. What property do you think that would be? If you flick back to the front side of your notes, what property do you think that would be? All right, it is the multiplication property of equality. Oh, M-U-L-T, property of equality. Let's look at B. If 2x plus 3 equals y, and y equals 5x minus 7, then 2x plus 3 equals 5x minus 7. So look, both of these were equal to y. And so then they just said, well, hey, then they have to equal each other. What property is that? Okay, so you could call it the transitive property of equality, or that is the substitution property. Okay, so I would take either of those, the transitive property of equality or substitution. How about the next one? If p minus 7 equals 10, then p equals 17. Well, that's a lot like, C is a lot like A, but this time we're doing addition. So it's the addition property Excellent. It's the addition property of equality. We'll put a period there for equality. And the last one. If 4t minus 1 equals u and t equals 8u, then 4 times 8u minus 1 equals u. Okay, so again, we have equals u here and it equals t. That's what's helpful. They took this t and they put it into here. So now we have 4 times the quantity 8u minus 1 equals u. That is the substitution property. Good. That is the substitution property. Very, very nice. Okay. Then let's look at the definition of a proof there. It says a proof is a system of reasoning or argument to convince a person of the truth of a statement. So you're trying to convince them of the truth of a statement. Algebraic proofs are a series of connected algebraic statements with their supporting reasons. They do need to be connected, right? They have to be connected. And I've told you that those start this chapter. And so we are there today with example 2. So example 2 says prove if negative 3 times the quantity x plus 6 equals 6x, then x equals negative 2. All right, so the first thing that we do in proofs, all right, that first step here is we write what we know. Okay, that's what they have given us. And then the reason that we have there is, well, it's given, right? That was given to us, or it's the premise. But we don't really write premise, we just write given. Okay. All right, so then we need to come up with our next step. Well, our next step, let me erase this a little bit so it doesn't get too cluttered. Our next step would be to actually do the math. Okay, we're going to distribute. So we'd have negative 3x. Negative 3 times a positive 6 is going to be a negative 18. So minus 18 equals 6x. All right. Well, we just did what property? The distributive. So that's our reason. We did the distributive property. I will abbreviate these most often, but I didn't. All right, next, I actually gave you the reason. Okay, we're kind of filling in the blank here. It says addition property of equality. Well, if we added here, so let's say we have an x, the 6x over here. So let's add a 3x here. Let's add a 3x to both sides. We're going to write our answer. So we're going to have negative 18 equals, oh wait, no, sorry. Let's actually, the addition property of, whoops, is the adding 3x. I didn't make it big enough. So we'll have, it kind of depends on how you look at the book. I'm going to write plus 3x here and plus 3x here like we're solving it as the addition property of equality. The simplification is going to be negative 18 equals 9x. Okay. Sometimes, like if you would look in the book, you see that they have you write out this whole new equation for number 3. I'm not going to do that so much. Like if you can show me the step and then tell me what it is, I'm good with that. All right, so simplification. Perfect. So now we're at negative 18 equals 9x. What do we need to do next? All right, so some of you might say divide by 9. The only problem with that is we don't have a property. So what's the opposite? Like what did we say division was? Okay, it was the multiplicative inverse, or the multiplication property of equality. So if we would multiply by 1/9, okay, we can multiply by 1/9, which is the same thing as dividing by 9. Okay, but this is the multiplication. So multiplication property of equality, so EQ. And that's going to leave us with a negative 2 equals x. And what did we do there? All right, we simplified. So that's simplification, just like we had in step 4. Okay, now here's the thing. Number 6, I have negative 2 equals x. We're supposed to be proving that x equals negative 2. And yes, it matters. So we have to change this to be x equals negative 2. And what property allows us to do that? Excellent, the symmetric property. So this is the symmetric property of equality. So the symmetric property of equality. Awesome. So hopefully that's kind of a nice ease in to some proofs for this chapter. All right, because we're going to have another one. If you flip on to your next page, page 3 there. Oh, there it goes, it cleared. All right, example 3. We are given the figure with x, y, z, and xz equals 35. Solve for b and justify each step. Yikes. Okay, but remember, the first step is given, right? The reason is always given. So what did they give us? What information? Well, they gave us this x, y, z, and xz equals 35. So x, y, z, and xz equals 35. All right. Next, okay, because again, we're kind of filling in the blank a little bit. Reason 2 says definition of between. You may have to flip back into your notes, okay, to find the definition of between to help you out there. But the definition of between is that xy plus yz equals xz in this case. Okay, so it's like we're taking x and y and adding them together, and y and z adding those together, and it's going to give us the total of xz, which would make sense. Because you have to remember that this notation, that x dash y dash z, is notation we use for betweenness, or when they're between each other. So we're pulling from that, and this was chapter 1, that betweenness. Okay. Step 3. So I have 4b plus 3 equals 7b minus 1 equals 35. Okay, so these values came from here. They gave us this picture, and so these values came from here. But I put them in like xy is equal to 4b minus plus 3, and yz is equal to 7b minus 1. And I know xz was equal to 35 up here. So what property did we just use there? Excellent. Hopefully you got substitution. We just use substitution to put those numbers in where they belong. Okay. Next up, we should be able to do some simplification, right? There's no distributive property. We don't need these parentheses, so we can add like terms. So we have 4b plus 7b. So that's going to give me 11b. And then I have a positive 3 minus 1. So that's going to give me a positive 2. That's a 2, not a z. Equals 35. And I just combined like terms and made my equation simpler. So my reason for this is simplification. Good. These are my favorites, right? When I'm like, oh, I know these properties. I'm just simplifying. I'm just substituting. Woohoo! Okay. Next up, if we subtract 2, this one's going to be a little different. We would end up with 11b equals 33. So we can say, well, what property? Instead of breaking this down into 2, again, we did subtraction. But remember, subtraction is the same thing as the additive inverse. So this is the addition property of equality. And so I'm going to put in there subtraction. Because it's the inverse. And then we divide by 11. Okay, this is making your proof a little bit shorter by just putting the step at the end. So b equals 3. So we divided by 11, but remember we can't call it that because it's the same thing as the multiplicative inverse. So this is going to be the multiplication property of equality. But we did, again, I'm going to write division out here on the side because it's the inverse of division. Okay, so we solved for, let's see what we did. We solved for b, check. And we justified each step, check. So again, it could have been 8 steps if we did the addition property of equality for step 5, and then step 6 was simplification. And then step 7 would have been multiplicative property, and step 8 would have been simplification, like we did on the previous one, but we can make them a little more compact. So next step for you then is the on your own at the bottom. And so you do have one to state the most specific proper subset. So are these integers? Are they whole numbers? Are they rational, irrational? And then can you complete the proof? Can you give me the reasons for this proof here? Okay. All right. I will see you tomorrow. Don't forget your homework's on the front side. And good luck.